Okay, so good morning. It's another 8:30 on a Monday. So today is February the 9th. I imagine a pretty quiet week for us, but I imagine you guys have a lot of, or traditionally, this is a midterm season. There is an assignment too that is due after the break, so don't forget about that. But otherwise, we're pretty quiet. Oh, I think I even forgot to. You might even be able to still get tutorial 3, and I believe I forgot to take that down. So, well, whatever. If you submit it, it's not late. I think that's it. Questions about the yeah. Probably, well, ideally after class, but I teach another class and then I might forget. I don't know. We'll see. Why? You want to try and get it up? I leave it up for the rest of the day. I can leave it up till tomorrow morning. That's yeah, sure, no problem. Other questions? Okay. Last class we were talking about sort of the new design using object design categories. So with assignment 2 and moving forward would look something like this, right? So we have a control class that manages what's running when. We have a boundary class or a view class that manages the interactions, in this case with the user, but it doesn't have to be with the user. In theory, it could be with a web service or something like that. And then we have the university, which sort of represents all the data we want in our application, all the data that we want to manipulate. And university contains some students. And now this is kind of a UML diagram, which we're going to get into today. It's not exactly perfect, but we do have arrows we can see going from control to view in university. That means the control or controller contains the view in the university. And we see multiplicity indicators here, which means that they contain one of each. Whereas the university down here, we can see that it contains students, and the star means 0 to many. Okay, so just a little preview of what we're going to get into later. But the one thing, we did write some of this code, right? And we were sort of writing at increased layers of abstraction, right? So now instead of the university just managing raw arrays of students, we use a list class that manages all we encapsulate those details away so that we don't have to worry about them in the university class. Of course, in the university class, we are still at the level where we have to manage the memory, right? So even though we can store our students, we still have to decide as the university class when they should be deleted. And then at the sort of the top level is the control, where I don't really have to worry about memory whatsoever. I just say like, oh, university, you do this, and view, you do that. But the one thing that we didn't quite finish is that, so we did write some of this code, and we did run it, and it did, print out a menu, and we were allowed to add and remove students. And here you can see I've been running it with Valgrind. So currently, if I print out all the students, there are 0 of them. So if I add a student, A1, 1, and then I print out all the students, there we go, I have a student. And if I exit at this point, well, I have a memory leak, right? Because I didn't really manage. I created that student, but I never deleted them. So if I look at my university, my add student function does have a call to new here, right? If somehow the add fails, I delete that student, but otherwise they're added and not deleted. My call to remove has a delete, which is good, but I didn't actually remove the student when I exited. So when my university goes out of scope, I really want all those students to be cleaned up, which means I'm going to, in here, I am going to delete all the students, right? So I believe I called it students. Oops, I missed a letter. What is it? Size? What is my list? Get size. Okay. I thought it was get size. And then, well, the get function in my list class returns a pointer. So I can get each student by index and then call delete on that pointer. And that should clean up all the memory. Right, so delete students I, oh, sorry. Geez Louise, I am mixing up my paradigms here. So delete students get I. Now that's going to return a pointer. And the other thing it's going to do is, well, now I have a list of students, of course, that still has the same size. I didn't actually remove any of these students. But my list is completely destroyed now, right? I've deleted everything in it. And so this is like not a great state to leave your list in. But at this point, I don't care because I know my list is going to get destroyed next, right? As soon as I exit this university, my list is going to get deleted. And then I don't have to worry about the fact that all of the pointers are to deleted memory, right? So that just to say that this is kind of a dangerous operation if my list was still hanging around after that. I wouldn't want to do things this way necessarily. But now I can add a student, A11, and then if I just exit, well, no memory leaks, no double freeze, no segmentation faults. So that's we're in good shape. And each layer of abstraction kind of has its own responsibilities. And well, one thing you might notice, if you get, and I can't remember if it was this class or the other class, but if you get a bug, now it's kind of a pain because now you have to go through the different layers and figure out exactly where this bug is occurring, right? Whereas if you sort of have a flattened structure where like, you know, sort of like bad design where everything is in one, or a lot of code is in each function call, well, then you have all the context. It's kind of easier to debug. The advantage of adding these layers of abstraction is that, well, really I should be testing each layer as I go so that I can be a little more certain that there are no bugs, right? So I would have some unit tests for the student class, and then I would make some tests for the university class. And then once I was confident in all of those things, then I could hook them in with the controller and the view. But anyway, that's basically where we left off last class. Questions? Okay. So yeah, let's do a quick woo clap to near B, right? So just on software engineering in general. So this, it's not going to be too difficult, but yeah, just to see who's all here on a Monday morning. Yeah, it won't be as. Of course, this is software engineering stuff, which is more about the process than any technical features of C++. So these won't be technical questions, but all right, I think we're good to start. So which of these low-level design choices helps us write modular code, right? I mean, could work on the, trying to think of the correct way to word that, but so this is what I settled on. Hopefully you get it. Which of these would I use at a low level to help me write modular code? And I mean, I don't know, just you can make a pretty strong argument for any of these, right? I did again. I don't think I captured what I was trying to say very well. So just do your best. But But if we went back into the notes, we would see that low-level design, we talk about encapsulation, abstraction, and the principle of least privilege. So those three are definitely the things that we keep in mind at a low level. We try to encapsulate whenever we can. We try to provide, a nice layer of even just a small layer of abstraction even on a class API, let's say. And the principle of least privilege helps to sort of guide us in those things. Use cases in testing are actually closer for high-level design, I suppose. But again, this is kind of semantics, right? You could make an argument. Match levels of testing to their description. So we did talk about 3 levels of testing. So what are their descriptions? See what people are saying. Yeah, so integration and systems seem to be where some of the confusion lies. Oh, somebody unit testing, yeah. Again, it's difficult, it's not like C++ where something either happens or it doesn't happen. Some of this is subjective, right? You could if you're interpreting one way, then it could mean one thing, and if you're interpreting another way, it could mean another thing. But generally, at least in this class, when we say unit testing, we're talking about the lowest level of testing you can get to, right? So generally, individual classes or even individual functions. Systems testing or integration testing would be, I want to integrate some classes together. Now, they might exhibit some more complex behaviors, right? So it's going to be a little harder to test. And then systems testing is, of course, testing the system as a whole, which is even more difficult because now you have like a lot of emergent behavior and things like that, and bugs that you would not expect. But so yeah, generally speaking, that's what we mean. But of course, if you said something else, that doesn't necessarily mean you're wrong. It's just you understood things a little bit differently. Which of these is helpful during the requirements analysis phase of application design? See, I'm trying to experiment with getting more marks out of this section, the software engineering section. I just don't like it because it's subjective stuff is, you try to mark it as best you can, and then people argue about it, and it's like, well, you kind of have a point, and I hate getting into that big mess. But it is, I guess, still maybe useful to go over. So requirements analysis, specifically, we did talk about a few different phases. Requirements analysis was first, right? So what are we trying to build? What are the requirements? And then design, implementation, and testing. During the requirements analysis phase, we did talk a lot about use cases, which most of you got. Again, writing tests. So the way we describe it, not necessarily, but generally speaking, each use case gets associated with a test, right? So you say, I'm going to test. One of my use cases is I try to sign in and I get the wrong email. What should happen? And then I need to test that, right? So which of these statements about API design are accurate? I guess these are multi-select now, so you can select multiple ones. And by API, we just mean sort of whatever part of your code is public facing. It can be types, it can be functions, obviously a combination of those two things. Right? Like a date library would have a date class, most likely. maybe a time class, and then it would have a bunch of functions that you can use, like sort of print out your date in this format. APIs can always be changed later. So changed, again, subjective, right? So you cannot, every addition you make to an API is permanent, but you can always make more additions. So sure, we can accept number one. You should write your API early and often. Yes. That's going to help you flesh out exactly what it should be. Customers should be familiar with the implementation details of your API. Now, again, see, wording matters so much. But so what I was trying to say is that, well, basically one of the rules is that we should hide the implementation details. So technically this would be false, but again, based on the wording, you could have had a different interpretation. Writing a class means you're writing an API, yeah. So what I was looking for were these two, but of course, you can make arguments for any of them. So yeah, that's it. Questions on any of that? Again, highly subjective, which I still think it's interesting and worth taking, but it's harder to test subjective stuff. It's harder to trace it to a mark. All right, so, whoop, I did not mean to do that. What's resumed? Oh, right, there we go. Thank you. Oh, I hit the pause. All right, there it is. All right, so let's talk a little bit about UML, and then we'll get into some back to some coding. We are taking, we're going to talk a little bit about documentation in general, but not too much. I'm going to skip a lot of this. We're focusing on UML. This is an introduction to software engineering. UML is one of the sort of diagrams that you kind of should know. Now, there's a lot of other ones. I sort of have a thing that I do when people who graduate and get a job come back to visit. I always ask them, what design documents have you used? Or for instance, I'll say, do you guys use swim diagrams? And mostly the answer is no. Mostly documentation, as far as I could tell, is written in English. And these diagrams probably used with less frequency. But that's not to say the documentation is not important, and the ideas expressed are probably still useful. UML diagrams you will definitely see at some point, even if it's just on a whiteboard. But it is kind of fun to see what's the difference between what we teach and what people use. We want to introduce you to UML diagrams. That's the main purpose of this section. We're going to take a look at some other types of documentation and its importance. So someone who worked at Google, this was their description of their work week. They did 1 day designing a feature. They did 2 days of writing tests, right? I mean, this was like they write a feature, they go to their boss says, okay, write some tests. And they write some tests, they come back, and the boss says, okay, write some more tests. And then they finish that, and then he comes back, and then the boss says, write some documentation. And then on the second day, write more documentation, right? So that's, especially at a place like Google, you really want to make sure that you don't have a lot of there's a lot of these rules, a lot of constraints to make sure you don't, of course, break existing code. But also, everything that is part of the code base, people should be able to use and use well. So at a place like Google, they're going to be a lot more strict about stuff like this. Of course, why is documentation so important? And as much as it is kind of a pain sometimes to write documentation, it is very useful, right? When I write in Java, my goodness, I really like the documentation. I know if I Google any Java term, I mean, we have large language models now, but if I Google any Java term, I'm going to be taken to a Java doc. And that Java doc is going to have links to other things that I may need to know about this particular class. And it's wonderful. It's so easy. I've had other experiences with, I did a project that there was 2 mesh libraries available, and one was didn't work so well, and it was well documented, and the other one worked better apparently, or that was the word that I got, but it was undocumented. And so I went with the undocumented one, and that was, my goodness. Like you just have to kind of, it's just trial and error, and then guesswork, and it's just bananas. So yeah, you want good documentation, especially when you're putting out a library or something that other people will use. Also, like, you know, you're going to get to some point where you're looking back on old code that you wrote and be like, what did I do? What was I trying to do here? Also, right, teams change. So yes, you may have somebody that knows the code base very well that you can ask questions of, but they might go get a better job, and now you're stuck, right? So good documentation sort of helps to bridge that gap of changing of personnel. This is the software development lifecycle that we talked about, right? Requirements analysis, design, implementation, and testing. Each of those has documentation. This you will take in 3004, so I'm going to kind of skip over it. Yeah, let's skip over it. I'm falling behind a little bit, so I'm going to skip some of this stuff. Some of the stuff that I don't really test you on it anyway, so it's skippable, and you will take it in 3004. I do like, so implementation, self-documenting code I am huge on, right? It's really nice when your code reads well, because that's mostly what people are going to be reading. You may have some documentation, and I may spend time reading that. But if I'm, say, using or modifying your library, I'm reading code. So well-written code is fantastic. Tutorials are also sort of underrated. I think I am considering having an aspect where you have an application and then write a tutorial for it, because tutorial really helps you to flesh out use cases as well, right? So yeah, tutorials are like one of the single most useful things I find for a library, is if I have a tutorial that walks me through some partial implementation or a full implementation, then I can use that as a jumping off point. So testing, test plan, and test cases. Yeah, code should be self-documenting and read like pros. Test cases should describe. Now, you guys may have experienced some sort of documentation on your assignment 1 when the tests run and you're trying to read and see where things went wrong, and you get a good idea of like, hey, maybe that could have been better documented, right? And that's valid. Also, though, if I was writing tests for an application, I would spend a lot more time on them. But yeah, so when I run a test, it should say, here's what I'm testing, here's expected output, and there you go. The unified modeling language, this was, oh my goodness, I don't remember the history of this. But it is used during the design phase to help document your design. Yeah, we're mainly going to focus on UML class diagrams. All right, so something that looks like this. There are also, so UML class diagrams are primarily concerned with classes and objects and their relationships, right? So classes have attributes and operations, and then they have relationships to other classes. There are other diagrams, activity, sequence, that sort of, somebody did say they saw a sequence diagram in the wild. They worked at Google. They said they saw a sequence diagram, so there's one. I've never seen a swim lane one, though. State machine diagrams as well. But here's a sequence diagram. You're not going to need to know this, but just as a sort of an introduction to other types of diagrams that you might see in, well, you will see in 3004. But this indicates sort of the control flow of your program, right? So your client is running first, or at least there should be, I think there might be something missing here. Your client is the first thing to instantiate. It makes a new concrete builder, which runs this little piece of code here, and then it comes back, and then we get a new director, so it initializes a new director. And then I call on my director object, I call the construct function, and then the director runs for a while. Right, so you can sort of map out what is running at what time and the life cycle of some of your objects. Activity diagrams. So this is a sequence diagram. Activity diagram is, you know, a flow chart. Yes, no. Yes goes one way, no goes another. State machines. These are quite a lot of things can be modeled as state machines. So a state machine diagram would look something like this. I don't want to go into it in too much depth, but if you think of what a pop machine does, that's like a state machine, right? This, you know, back when you used to actually put money in instead of tapping your card, it would maintain a state of, say, well, somebody has put in 20 cents so far, right? That's the current state, and then now based on what you do, it's going to choose to do something else, maybe give you a pop and give you change or whatever. All right, so let's dive into, again, so when you, for assignment 3, when you're making your class diagram, this will be sort of the specification for how to do it. Okay, so there's a lot of different specifications out there. But yeah, we'll just provide this one. Ours is a very simple sort of subset of UML diagrams. So rather than looking through an entire document, we'll just do something like this. We're going to be modeling classes and associations between those classes. Classes consist of name, right? The class name, a set of attributes. So here we can see the attributes, which are just member variables, essentially. Operations, which are functions, and access specifiers, right? So one of the keys of object-oriented programming is encapsulation, and that is largely due to access specifiers. Now, this is not specific to C++. This works with any object-oriented language. All right, so, right, this is sort of what I just said. So yes, class name, here are 2 attributes, home and away. Those are both strings. And then an operation, which is a function. Yeah. Attributes, well, all attributes and operations start with an access modifier, right? So these are private, protected, and public, followed by the name of the attribute, followed by a colon, followed by the type, right? So it's going to be a little bit backwards from what we're used to. Right, so string is going to come after the name of the variable. I mean, why? I'm not exactly sure, but maybe the name is more descriptive. And that's the thing about the UML as well. These should definitely describe, you know, it's not really important that the variable names are exactly the same, but this should be very descriptive of what this variable represents. This is a communication tool, right? So we don't want to leave things ambiguous. In general, there are a couple other tips. Abstract classes and methods are shown in italics. We haven't gotten there yet, but we will. Static members are underlined. So here, we haven't gotten there yet, but we will. Friendship associations are never shown. Friendship is specific to C++, so it's not part of object-oriented in general. We haven't taken friendship yet. We're going to get there shortly. Operations syntax, similar. We start with an access modifier, followed by the name of the function, followed by a parameter list. And each parameter list is basically a declaration of a name and a type, but also this in, out, or in, out, right? So we talked a little bit about input parameters, and we talked about output parameters, and we probably briefly mentioned input and output parameters, which you pass some information in, and then it's modified and passed back to you. So we're going to specify those types of things. And those are, yeah. After the parameter list, we put a colon, and we put the return type. If there's no return type, if it's void, we could just leave it blank as we did here. We are looking at 2 main relationships, right? There are others. Well, there's like a uses and probably some others, although I'm not really refreshed on my UML knowledge. But we're looking at composition and inheritance. So composition is the HAZA relationship, where one object is sort of contained in another object, Now, whether I might contain a pointer to that object instead of the object itself, but that still counts. So yeah, in this case, it's a has-a relationship. The container is a class that contains another instance of another class, and the containee is the one that's contained within the other class. You can see here that, well, so if I had written it like this, then this would be a hockey game contains two hockey teams, essentially, right? So we're going to follow the direction of the arrow. If there is no arrow, then it's sort of, you can think of it as a two-directional arrow, right? So the direction is which class contains which. So if I have a one-way relationship here, then I use the arrow. If class A contains one or more instances of class B, then I have an arrow from A to B. And then at the end of that arrow will be the multiplicity indicator, some value or range we'll talk about in a second. If both classes contain instances of each other, then we can leave out the arrow, right? So in this case, we have a hockey game that contains two hockey teams, and each hockey team has a schedule of many hockey games, right? So that's the relationship here. Multiplicity, generally, right? Zero, well, I guess 0 is probably not that common. I can't imagine an instance where that would be necessary. Although you can include 0 as part of a range, right? I might have something like this, 0 to 5. So I can contain anywhere from 0 to 5 of a thing. This star means many, and we could do a range like this. Of course, this is equivalent to this, but we're not going to be super picky about that sort of thing. Either of those would be fine. We never have multiplicity indicators on inheritance, only on composition. Right, so here we go. A hockey league contains one hockey schedule. A hockey schedule contains one to many hockey games. Each hockey game contains two hockey teams, and each hockey team can be in many hockey games or contain many hockey games. And then the number of players on a hockey team, there's 5 up to however many you want. And each player belongs to one team, right? So we can define all the relationships that way. We don't explicitly show collection classes. I used to be sort of strict about this. I've gotten less strict. It's not a big deal. I don't know. But generally we don't, right? That's sort of a low-level implementation detail. At this stage, I shouldn't be concerned whether this is stored in a list or a vector, right? That's not a consideration at this stage. So we also model inheritance, right? So the inheritance is an is-a relationship. So we might talk about a superclass or a parent class or an ancestor or a child or grandchild or those sorts of things. So in this case, the child class, in some sense, points to the parent class. Now, I don't want to say points here because I believe syntactically, some people would argue that that's not an arrow, it's a triangle. And so I don't know. I try to avoid semantic arguments, but yeah, so we'll call it a triangle, right? So and also this sort of make sure you don't confuse it with the arrow, which is composition. So a triangle is attached to the parent class or the superclass, or points to the superclass. So we have, for instance, NHL employees, and they may be a hockey player is an employee, a coach also is an employee. A defenseman is a hockey player, which is an employee, and an assistant coach is a coach. So the higher up we get, the more generalized classes, and then lower down we get more specific. In terms of sort of left this ambiguous because, right, if in this case player inherits from person, then person has these, I should update this one here, but here it's written, so we're going to keep it this way, but person has these functions. Now, player inherits these functions, but in this case, this would be an abstract function, which means that player would have to override that. Regardless, it's fine. However, if you want to put these functions in your player class, that's okay. I did not here. That's also okay. So it's kind of up to you. Generally speaking, remember that if I'm writing a UML diagram, it's not so that I can brag about meeting the exact specification. It's so that I can communicate something. So make sure your diagram communicates something. Don't show do's and don'ts. Don't show constructor or destructor or getters or setters. These are, again, low-level details. This is not the scope to be examining those things. And collection classes. Again, we don't really care how the team stores its players, and that might change. But we do know we need a team and a player. Of course, don't do this. We list as attributes primitives and strings, which are not really primitives, but we pretend they are. The actual, if I contain, let's say, an address class, well, then I want to represent it using this contains relationship because, the address class itself has all this information. So when I'm modeling composition, I want to make sure that all classes are modeled using the arrows, and then primitives are modeled using just attribute lists. And that's it for UML diagrams. So these were made using draw.io. That is a nice, easy. I mean, it has its problems like every other application, but the nice thing is you can download it from the Windows Store. You can download it from the Ubuntu Software Center. I'm not sure on Mac. I'm probably available, but worst comes to worst, you can just run it. In your browser. Please ensure just right. So here we go. So it's very versatile. You can use whatever you like. You might have your favorite tool. All right. Questions? Okay, so there's no woo clap for UML diagrams. We're going to move on to encapsulation. So this sort of it's a broad subject. And so, again, it may be kind of arbitrary, some of the things we put in there. But we're going to talk about composition, right? So, well, the thing is, when we have a class that contains another class, that class still deserves its privacy, right? So how do we overcome the fact that some of my member variables have private members themselves? We're going to talk about constants. So consts, the const keyword is what we use to sort of protect a lot of our member variables and classes from abuse by verifying with the compiler that they're used correctly. And then we're going to talk about friendship. So friendship violates encapsulation, but of course this is C++, so sometimes that's important. We'll talk about static class members. This is all well, constants. Yeah, some of this is assignment 2 stuff, some is assignment 3. Composition is when one object contains a member variable that is an instance of another class. In this case, we have a student, and the student has an address. And so if we represent the address as another class, well, and we statically allocated the address within the student class, well, then if we looked at memory, it would look something like this, right? I would have a student that is all of this, but part of the student would be just the address stuff. So we're going to see, well, that looks fine when I look in memory, but actually this is all private to my address. So how does my student and address interact with one another? We're going to basically solve that problem. Yeah. All right. So yeah, Well, let's just take a look at it and then we can come back to that stuff. All right, so I'm just going to make a student. Now, if I look at my student constructor, it's pretty long because in addition to the student information like number, name, GPA, etc., I also have this address information, right? And I have some default values for that. And really, yeah, all right. So I have a big long parameter list, and so in my student, I want to make an address member. Okay, so I'm going to statically allocate an address, a member of the address class. Now, if I look at address, well, luckily, I have all default values. So I have a default constructor. We'll see why that's going to be important. But I'm going to make a student and I'm going to print out the student. Now, if I look at the student constructor, yeah, I have to be able to initialize all of these things. So I want this number equals number. This name equals name. This major program. Yeah, so actually, major program equals NPM. Okay, so this is something we may have mentioned before, but of course we use this if there's a naming collision. If there's no naming collision, that we don't need to. And really, it's better if all this was consistent. Like, if I'm going to introduce naming collisions, then you know, this should be major program and this should be GPA. But and then I have to initialize my address. Now, my address is sitting there in memory the same way as when we statically allocated an array of things, for instance, dates or what have you. So you can think of it as an array of one thing. And how we initialized that in our assignment 1 was to make an address number, n, so number, street, city, province, and use the assignment operator to assign that, that address. And then down here, well, I want my student to print out, and I want the student to print out the address at the same time. And so, like, I might try to do something like this, right? Try to get the street number. Of course, this is, well, if I try to compile that. Well, it's not going to like that, right? Because this is private. So we do have the problem with encapsulation that suddenly accessing things is a bit more complicated. I can't just directly access the members of my address class like I would like to. So what I'm going to do instead is, well, my student knows how to print. My address also knows how to print. So I'm just going to say, listen, I trust that you know how to print yourself, right? The address class contains this behavior of print, and so I'm just going to use that here. Okay. So yeah, I cannot access the inner member variables, but I should be sort of calling on something in the public API, which in this case is very, very little. The constructor and the print and the destructor, which is called automatically for us. All right, so I should be able to make a new student and call print on them. And there we go, that works. So we have a student named Stu who's in computer science, and their home address is 123 Main Street. All right, well, again, we have this problem, right? Because you'll notice that in my address class, I mentioned when my address was being constructed, and I mentioned when it was being destroyed, so we can kind of get a sense of what is happening. And of course, my address is constructed twice. And then, so when I'm making a new student, my address constructor is called, and then I call it again, and then one of those is destroyed. So what happens here is that, well, actually, the same as when I statically allocate an array. The first thing that happens in my student constructor, or when I make a student, is the address is constructed first, right? So the address is constructed, and then here, let's make this absolutely clear. Right, so I make a new student, and as I'm making a new student, the address constructor is called, and then the student constructor is called. All right, and if I want to use the old style, then I'm going to make a second address, which is this guy, and then this guy is going to get copied into my original address and then destroyed. So this is kind of wasteful. I'm making two destructor calls and two constructor calls and one destructor call when I really only want to be constructing this one thing here. So to solve this problem of, and also I cannot do this, which would also be a possible solution. Because again, this number is private to address. So I want to call the constructor of the address class, but I don't want to call it twice like I do down here. So I'm going to use this, I think I might be getting ahead of myself here, but it's all right. So I want to call the constructor on address. And so what I'm going to do is I'm going to use this, it's called member initializer syntax. So after the call or the parameter list of my constructor and before the body of my constructor, I'm going to list all the member variables that I want to pass arguments to their constructor. So in this case, the address takes a number, a street, a city, and a province. And all right. Okay, so this is exactly how I want my student to be created. As I'm making a new student, well, the address is created first. And then my student, I initialize all these member variables. And then when I print everything out, everything is printed out just fine, right? So I have a student that has all these members, and my address also gets initialized correctly. And then when I'm leaving, when my student is being destroyed, well, the student destructor is called first, and then the address destructor is called after, right? So for composition, yeah, in student constructor, did I not say that? Did I get too far ahead of myself? Yeah, so for composition, the thing that is contained gets constructed first, and then the student gets constructed after. And then when we're destroying it, it happens in the opposite order. The destructor of the student class is called first, and the destructor of the address class is called second. Right, and so this is kind of necessary because maybe inside my student class, I need this address thing constructed in order to properly initialize these member variables. But yeah, questions? Okay, and so if we want to properly call the constructor, we need to somehow access it before this code runs, because at this point, the address constructor has already been called. And so I use the member initializer syntax to say like, hey, I know you're going to construct the address before my student, but I want you to construct it with these parameters. Yeah, okay. So this member initializer syntax, so here I'm using it exclusively for the address, but I could, of course, do it for all of these as well. I don't really have to do any of this here. I can just do it here. So number. Now this is, here, I'm going to put this down on the next row so we can see everything. This is, of course, this number is the parameter number, and this number in yellow is actually the member variable number. So I do have a naming collision here. However, when I write it in this syntax, the compiler knows which is which, right? It knows that this is the member variable and that this is the parameter. So that's valid. I don't need the this qualifier. Name, I can do the same thing. Major program. And GPA. And then basically, if I wasn't doing this, I could simply have an empty constructor, and this would be fine. Let's try that out. So there we go. My student, when I print out my student, you can see that everything is initialized and everything gets constructed and destructed as it should. And so in C++, you often see constructors that look exactly like this. First of all, you'll see stuff like number, which might be confusing if you're not familiar with what it's actually doing. But these are actually two different numbers. One is a member variable, one is a parameter. And you'll see often just a parameter list and then an empty constructor, right? So that's perfectly normal in C++. And this is technically the best way to initialize all these things, right? It's going to be the most efficient. Now, we will accept either way, right? So if you can use a member initializer list, or you can do this sort of old school assignment way. Both are fine, even though this is slightly less efficient. Because when I get here, the constructor has already been called for this string. But if I call it up here, then I catch it before the constructor is called, and I give it an argument. All right, questions? Okay, there is one other thing I would like to show. So let's say that let's get rid of this. Let's go back to this, which is, slightly more inefficient, but it does work. Yeah, and then, but let's go to my address, and my address has all default values, but let's say that for whatever reason I decide, oh, I do not want to give you a default street number. So you have to at least give me a street number. And then I try to, well, I try to compile it and I get an error. So there's no matching function for address, right? So I no longer have a no argument constructor for the address class. So when I have a member variable like address that's contained in another class like student, I have the same sort of rule apply as when I make an array of objects, is that, well, this is going to have a constructor called on it, and if I don't use the member initializer syntax, it's going to want to call the default constructor, right? So if I just don't call any constructor on it, let's say. All right, this. I still get that same error. So a constructor is being called. It's looking for the default constructor. It's not finding it. But what I can do actually is, even without a default constructor, I can use this member initializer syntax. Because now I'm actually not calling the default constructor of this address class. I'm calling the for-argument constructor. So in this case, I have some, oh yeah. Did I mess up? Let's try. When in doubt, make clean. No, still nothing, no. Oh, yeah. So interestingly enough, because there is a copy constructor, I now run into that same problem with my copy constructor, right? So I've handled it here, but down here, when I try to compile this, it's looking for a default constructor for the address class, and it can't find it. So I will have to do this stu.address, right? So this will call the copy constructor of the address class and pass in the address of stu here. And there we go. So yeah, we have a student stu. So the member initializer syntax is the best way, the most efficient way to initialize your member variables. If you're using composition and you want to call something other than the default constructor, then you will use, the best way is to use this. There's also, you can cheat with the using the assignment operator also, but that makes an extra constructor call that you don't want. If you don't have a default constructor, then you absolutely must use this. Okay, so there's no way around it. In this case, address has no default. So if I do not call this like this, and also in the copy constructor, if I've made it, like if I've overridden the copy constructor, then it won't allow you to compile. Okay, so that's called member initializer syntax, and it solves the problem of the idea that well, the address gets constructed before the student, so how do we pass in parameters? Questions? Okay. Yeah, so we could invoke the copy constructor here, but we'll save that. All right, so in order to not violate encapsulation, right, we have all of these member variables, but technically these are invisible to my student class. They're part of the address class. Well, I still have access to the public interface of my address class, which means that, hey, if I want to print out the address inside my student print, I can just call it directly. Also, if I want to construct an address by calling the constructor, I can supply its arguments by using member initializer syntax, right? So like this. And member initializer syntax is in general the most effective way. So this is, generally speaking, outside of compiler optimizations, the best way to initialize things. Constructors are built from the inside, or objects are built from the inside out. So containee objects are created first. They're created in the order that they're declared in my header file, not in the order that I list them in my member initializer syntax, right? So in this case, although it doesn't always come up as important, but number would be constructed first, then name, then major program, then GPA, and then address, irrespective of what order I listed them here. Destructors, objects are destroyed from the outside in, right? So the container is destroyed first and then the containees in the reverse order of constructors. The reason for that, or at least one example I might give for that, is that one of your objects might be a file, right? And so I contain that file, but in my destructor, I want to save everything to that file. So it better still be around when I call my container constructor. If it gets destroyed before I call the container destructor, then I have a problem. I can't access that file anymore. So containers are destroyed first, and then the things that it contains are then destroyed because I don't need them anymore, essentially. So that brings us to deep copies. So this is a large part of your assignment too, is managing memory, and one of the things you're asked to do is a deep copy. We're going to look at a very simple version of a deep copy, but it gets more complicated on assignment 2. But let's say that I decided for a different way to compose my student and address classes. So maybe I put my address class on the heap, let's say. And now my student class, we have a name and a number and a pointer to an address, right? So they're technically separate in memory. They're no longer jammed together. And I have a pointer from the student class to the address class. So whereas before, if I wanted to make a copy of this class, well, it's simple. I just allocate enough memory over here, right? So pardon how squished it is, and then I just copy all of those values over there, right? Using the string copy constructor and the int copy constructor and so on. But it's very straightforward. I just take whatever sort of values are over here and I copy them over there. If I try to use a default copy constructor in this deep copy, well, what is going to happen is that I don't actually copy this address because it's not actually part of my student class. If I make a copy of my student class, I'm going to copy the address, the memory address of address, right? So now I have essentially a pointer that points to the same address as this original student. And we actually did see how that could be a problem, right? When we were looking at the list class, if I'm deleting, if both of these delete the address, well, then I'm going to get a seg fault or a double free error or something. And not only that, if one student moves, right? So this is Joe over here, and then I make a copy of Joe, but then I change his name to Bob and change their student number, but the address, if Bob now moves to from 123 Street to 124 Street, well, Joe's also going to move, and that might not be what we want. So what we probably want is something like this. So I make a copy of the student. I don't want to copy the address directly over. I want to make my own pointer, and I want to copy really shouldn't. Using address is kind of weird. I don't want to copy the address, the memory address of the address over. I want to make a copy of the address itself in memory, and then have my pointer point to that. Right? So that's essentially what a deep copy is. Now this is a rather simple version. They can get more complicated, but let's take a look at that. So address is exactly the same. I'm going to put Stu now on the heap just so that I can delete Stu when I would like to. But now instead of a statically allocated home address, I'm going to make a pointer. I'm going to go through and change a bunch of things about this. Now, I did not initialize home address in here. Normally, it would be here. But for now, let's just do this. Just make it easy. Home address equals new address. Number, city, or street, city, province. Now, only one call to new, only one call to a constructor, so this is okay, right? I don't need to use member initializer syntax for this, although we can, we'll see that later. But this is fine. No new address is made until I call new. Of course, down here, I also want to delete home address in order to properly manage memory. Then yeah, this yeah. So the address constructor and destructor are called there. We're just going to make a student stu. We will delete stu, and then we will move on to other things. All right, so making a printing stu, the student constructor is called, oh. I don't know why my, should be making a new address. Yeah, probably a clean step. All right, so there we go. So student, and then inside my student constructor, I make an address. I print it out, everything works fine. And then I destroy. Oh yes, I forgot to. This is my copy constructor, not my destructor. So there we go. That should all work fine now. All right, student made, address destroyed, student destroyed. Perfect, but everything works well. Let's say now that instead of deleting stu, I'm going to make a copy of stu. Now my copy constructor doesn't do anything special. It just does the same thing that the default copy constructor does, which is just copies everything over. Actually, let's do this. Home address equals stu. It was almost everything. So this is what our default copy constructor would do. So let's do that. Now, if I look at my code, I make a copy of stu. I can set stu's name to Joe. I can print both stu and Joe. And making a copy. So here is my student Joe and my student Stu. They both have the same address because Joe is just a copy of Stu, basically, with the name changed. Strange that I'm a little baffled here why we didn't get an error, but all right, let's send Joe to, well, we've added a function to the student class called move to. So move to a new city. Now my address is a little bit different also. I have a set city function. All right, so city is private, but this will allow my students to move to new cities. So we're going to move Joe to Montreal, and then we're going to print out Joe and Stu. Oh yeah, now I know why, because we didn't delete Stu, that's why. So when I move Joe to a new city, oh, I didn't write the move to, is that right? Move to, all right, so address, or what is it, home address. All right. Okay, Now we move Joe to Montreal. We see that Joe is moved to Montreal, but then when we print out Stu, Stu is also moved to Montreal. Because again, the big problem is they both have the same address. They're pointing to the same address in memory. And technically, I have not deleted Stu, so if I delete Stu at this point, I also get a seg fault. Because now, when Stu gets deleted, of course, it deletes the home address. And when Joe goes out of scope, Joe is statically allocated. So Joe gets deleted automatically. And when that happens, it tries to delete the home address again. All right, so let's make a deep copy. But any questions on any of that? All right, so the problem is, of course, or the solution is quite simple. In my copy constructor, instead of doing this, I kind of want to do this. Right, so this is going to call the copy constructor of the address class, right? And I don't have an explicit one, but I do have an implicit one. It's one of the free constructors that I get. Right, so address has a copy constructor. It's not visible. Student also has a copy constructor, but I've overridden it. So the default one gets deleted and student now uses this one. But home address does have a copy constructor, so this will work. And it will put a new address on the heap. And yeah, this is basically the only place I need to do it. So if we run this now, sending Joe to a new city. So here now Joe moves to Montreal, but Stu stays in Ottawa. And now we can see that when we delete Stu, well, the address gets destroyed. And when we delete Joe, the address also gets destroyed. So that's it. That's a deep copy. Now, if you want a deep copy, you have to write it yourself. You cannot get a deep copy. There's no default copy constructor that does it. This is a very simple version of a deep copy, right? So the one that you're required to do on your assignment is, I forget what you're copying, but there's going to be multiple layers, right? You're going to have a list of things. And then so you're going to have to figure out, how do I copy the list? How do I copy everything in the list? And make sure you manage all the memory while you do that. Okay. Questions? Okay. All right. So just a couple other things. Although I am doing everything the old-fashioned way here, I don't have to. I could still do something like this using member initializer syntax. If I call home address, well, home address is a pointer technically, and so I can initialize it with a pointer. And well, the new makes returns a pointer. So I can use member initializer syntax even with pointers and copy constructors. Right, so home address, new address. So there, I have, using member initializer syntax, I can still do deep copies if I'm so inclined. You don't have to do it that way, right? So there are times where you do have to use member initializer syntax, but we're pretty flexible about it. You don't have to if it, I said, as long as you're not making two constructor calls of a member variable, right? Now, technically, you're making constructor calls of strings and ints and things like that, but so we'll kind of ignore that. But as long as you're not making two calls to the address constructor, for example, when you only need one, then you're fine. So what we didn't show is actually if we did something like this. So instead of making a copy, right? Well, if I do something like this invokes the copy constructor. But if I do something like this, this, of course, invokes the assignment operator. And then we end up with the same problem. So again, if I make Joe and then make a copy of Joe and Stu, and then I move Joe to Montreal, well, now Joe is actually named Stu now, and both are in Montreal, right? So writing, this is the assignment operator as opposed to the copy constructor. And now we can see we run into the same problem, which this is our rule of three, right? So we don't know how to write an assignment operator or override it, but when we do, if we write a copy constructor in the student class, then we probably also want to add an assignment operator that does the exact same thing. Because here we're running into the same problem where now we have two students pointing to the same home address. So yeah, the rule of three states that, well, if I need a copy constructor, well, then I probably have some dynamic memory, and that means I need a destructor, and that means I need an assignment operator because this one is no longer working correctly. So we'll get to assignment operator later in operator overloading. But yeah, that is part of the problem. Yeah, and then the rule of five, right? So we might touch on actually move constructors and assignment operators. Someone requested them. I'll see if I can fit them in. Maybe not, though. We are kind of short on time. But it does basically the opposite. Yeah. So if this was a move constructor, right? So here, this is what a copy constructor would do. But if it was a move constructor or a deep copy would do something like this, but a move constructor would just say, well, this is now pointing to null, right? So I'm going to break this. And this second Joe over here will steal the address from the first Joe. And the first Joe is probably going to get deleted. So that's why we would want a move operator. Because technically we want to make a copy, but the old Joe is going to be deleted. So rather than make new resources, I'm just going to steal old resources. All right. So we're going to talk about the const qualifier next. It has a lot of uses. Basically, it's going to make things constant. So you've heard of constants, but that, of course, has a bunch of impact on the code that we write. One of the things it has an impact on is the type of compiler messages we're going to get. Once we start introducing const, we're going to see a lot of things referring to L values and R values. All right, so let's talk about what an L value is and what an R value is. Loosely speaking, it's what can go on the left-hand side of an assignment operation versus the right-hand side of an assignment operation, right? So, or here, for example, L values can go on the left-hand side. R values can only go on the right-hand side. Technically, I can put an L value on the right-hand side as well. But R value means constant. It can't go on the left-hand side. I can't assign it anything. Now, this seems like probably a very simple concept, but of course, it means that stuff like this is not allowed, right? A plus B just returns a value. I can't assign it a new value. So A plus B is an R value. You cannot write to it. And returning by value, that technically is also an R value, right? I'm going to return a student, but you're not going to be able to make any changes to that student. You'll be able to copy it into another student or something like that. But yeah, so yeah, I guess we don't really have time to go any further. We're going to stop there today. So next class, we'll talk about const. Const is actually quite a big part of your assignment too. Right, we are going to const basically everything you possibly can, well, within reason. You will actually be given a list of things that you should make const, and then you can add to that list if you like, but that's up to you. So we'll stop there today. Next class, we'll we'll get into constant.